In this video, we'll be discussing the relationship between two separate variables. In the first section, 4.1, we're first going to define variables on where they belong in the graph. The response variable will be the y. This is the variable whose value can be explained by the value of the explanatory or the predictor variable. So the explanatory, which is the x, is also called the predictor, where the response will be y, and that is explained because of the x. In other words, the explanatory variable helps explain the variability in the response. A scatter diagram is going to be a graph that shows this relationship between these two quantitative variables, and they're measured on the same individual. Each individual in the data is represented by one point in the scatter diagram. The explanatory variable is on the horizontal axis and the response is in the vertical axis. Two variables that are linearly related are called positively associated when above average values of one variable are associated with above average values of the other variable, and same for below. In other words, as the value of one variable increases, the value of the other variable will also go up. Two variables are said to be negatively associated when above average values of one variable are associated with below average values of the other variable. In other words, as one variable increases, the other variable then will decrease. So let's look at some examples of what we just discussed. Here we've got a few different relationships. In the first relationship, we have what is called positively linear. First of all, we say the word linear because they are related in a line format, a straight line linear. Also, they are positively related because as the explanatory variable gets bigger and bigger and bigger, the response also results in a bigger value. So as explanatory gets bigger, response also gets bigger. So they are both going up together. Maybe not at the same rate, but they do increase at the same time. This is what we would call negatively linear. Again, it is linear because it does represent a straight line, and they are negative because as the explanatory variable gets bigger and bigger and bigger, the response is getting smaller and smaller and smaller. So as one gets bigger, the other goes the other direction. This is also related, but it doesn't seem to be linear. So there is a relationship, but since it has this curved fashion, it is not linear. Even though we could predict the next value, it is a non-linear relationship. For this chapter, we will only be discussing linear relationships. Same thing with this explanation over here. This also does seem to have a relationship between the explanatory and response variable, but it is also not linear. It seems to have a curved or maybe a cubed type of relationship, if you remember those graphs from college algebra, but it is not linear, therefore we won't be discussing either of these types. This last example has no relation at all. There is no predictor that when I put in a particular explanatory variable, I will be able to accurately predict what the response will be. They are completely scattered with no type of relation. So let's look at an example. Below is a table of data from a survey of 20 past statistics students. They were asked, how many hours do you study or do homework each week? And also, what is your GPA? Which variable would you think would be the x-axis or the explanatory variable, and which one do you think would be the y-axis or the response? And let's draw a scatter diagram. first let's do it by hand, then we'll also show you how to do it in Statcrunch. So if I were to do this by hand, a scatter diagram has an x-axis and a y-axis. So we were asked, which of these two variables do you think would be x and which one would be y? So x is always going to be your explanatory variable. Some people like to call it the independent variable. In other words, it stands alone, and it will drive a response in the y. So the y is what we'll call the response variable. Some people call it the dependent variable. So which of these two do you think is the explanatory versus the response? Well, if you said the number of hours you study is the explanatory, you'd be correct. So we're going to put hours studying down here, and then GPA will be the response. So what we're going to do now is we're going to plot these points. The hours studying can range anywhere from 0 all the way up to, it looks like the biggest number on here is 25 hours. So we have to at least go up to 25. So I'm going to break these up into segments. So we got 5, 10, 15, 20, and 25 hours studying. And the GPA can range anywhere from as low as, I could go as low as 0, but it doesn't seem to go that low. So let's go as low as 2, a GPA of 2, all the way up to a GPA of 4. Okay? All right. So let's put in the data. You can see that we have, for this person that studied 8 hours, their GPA was a 3.0. So somebody that studied 8 hours, their GPA was a 3.0, which is right here. This is 3.0. So we have 2, 3, and 4. Let's do the next one. If somebody that studied 10 hours, their GPA was a 3.4. So 10 hours, their GPA was a 3.4. So at this point, I'm going to let you pause the video and fill in the rest of the graph, and when you come back, I'll have this all completed. Okay, so I did go ahead and I completed the rest of this. You can see that we had all of these data points created on the scatter diagram, and you can see there does seem to be a relationship. I would definitely say this has a linear type of relationship, because it does seem to follow this straight line prediction. Let's go ahead and see if we can determine how we could do this in Statcrunch. Okay, so I went ahead into Statcrunch and I put all of the data that was from our table, from our lecture notes, into Statcrunch, as you can see here in the first and second column. So the first column, we're going to call the first column hours studying. And let's call the second column GPA. Then we're going to go ahead and we're going to go to our graph and scatter plot. So once we put the data in, you can see that the x variable needs to be the hours and the y variable needs to be the GPA. And if you don't put those in the right order, then your x and your y axes are going to be backwards. There are a lot of other options that we can do within here. Let's just go ahead and leave it as is for now. We'll just compute and see what it looks like. So here is the scatter plot. It looks very similar to what we had in our notes. Remember, this is what we did in the notes earlier, and it looks very similar to that. So Statcrunch does give a good relationship. It looks like a linear relationship like we said earlier. We could also put titles in here, which it already did because we already titled our axes up here. So it automatically took those words and put them as our x and our y axis over here. But if you didn't have that, there are ways to do that by going to your 3 lines down here in the corner, and you can put your title and your axis titles on your picture as well. You could also paint it and do other cool colors within each of your graphs as well. One other thing I wanted to point out is you can force this to actually intersect at 0 if you want the axes to both start at the origin. The way to do that is to go to your x-axis and make sure that starts at a minimum of 0. You could even start it as a negative if you wanted to. And we would do the same thing, and we would force it also to do that for the y-axis as well. We'll start at 0. So when you do that, you can see that these both start at the origin then. So it looks like this linear relationship is a lot higher because we didn't have any data in the GPA range from 0 to 1 or 1 to 2. Most of our data was from 2.0 and up. Okay, resuming back to the lecture notes, you'll see that we're now going to be talking about what's called the linear correlation coefficient. The linear correlation coefficient is a measure of the strength and the direction of the linear relationship between these two variables, x and y. The Greek letter rho represents the population correlation coefficient, and r represents the sample correlation coefficient. Again, as I noted in the previous chapters, we generally don't have population information. It's too hard to obtain that. So most likely for the remainder of most of the problems, we'll be dealing with sample information. In other words, for this case, R. R is going to represent the sample correlation coefficient. And the formula for this is as follows. What you're going to need in order to find the sample correlation coefficient is you're going to need x bar, which is the sample mean of the explanatory variable. You're going to need the sample standard deviation of the x. You'll need the average of the y, which is the response variable. And you'll need this standard deviation of the y response variable as well. You'll also need to know n, the number of individuals in the sample. You won't actually need to find r by hand. We will actually find this in Statcrunch. To do all of this in Statcrunch, which you could do by hand, we're going to do this in Statcrunch, which I'll show you an example in just a moment. Let's first talk about some characteristics of this. Some of the characteristics of the correlation coefficient is that the linear correlation coefficient is always between -1 and 1 inclusive. In other words, r is always going to be greater than or equal to -1 or less than or equal to 1. 0 is included. If r is a positive 1, then you have what's called a perfect positive linear relationship between the two figures. For example, this one down here, this would be a perfect relationship where r is positive 1. It is positive because it goes up with a positive slope, and it is 1 all the way at the maximum of 1 because it is a perfect relationship. In other words, I know exactly if I have an explanatory variable of some quantity, I know exactly what that's going to give me for a response. Each dot lies directly on a line and is not scattered at all. On the flip side, this would be an example of r that is -1. In other words, it has a perfect relationship. It just happens to be negative. It has a negative slope. It is perfect because the absolute value of this is 1. 1 would be the largest value you could have, and it is also perfect. The closer that r is to 1, the stronger the evidence of a positive association between the two variables. So these examples right here are examples of relationships but don't happen to be perfect. So in other words, this one does seem to have a linear relationship, but it is not perfect like it was in this graph. It's a little bit scattered. I would call this a strong positive relationship, but it is not perfect. It will have an r value of something close to 0.9. So close to 1, but not exactly. So it'll be more like 0.9. This is also a positive relationship. I do see as the explanatory goes up, so does the response in this linear fashion. However, it becomes a little more scattered in this graph than it was in this one. Certainly it's not perfect. So we would call this a positive, moderate relationship. It would have an R closer to 0.4. On the other side, the closer that R is to a -1, the stronger the evidence is of a negative relationship, such as these two examples down here. This has a negative linear relationship, as does this one, but these certainly are not perfect like they were in this example over here. This one would be strong, this one would be moderate. A strong negative relationship would have an R close to 0.9 negatively. This would be a moderate negative relationship, which would have an R closer to -0.4. You can see the closer we get to 0, the more the relationship doesn't exist, which means there is little or no evidence of a linear relationship between the variables. This would be an example of an R of 0. Meaning it has no linear relationship. It is completely scattered, non-predictable. Even though this does have a relationship, I can definitely see where the next data point is going to lie. It's pretty obvious what's going to happen with it's going to be cyclic of some sort, but it is not linear. R's only measure linear relationships, so this is also going to have an R close to 0. Even though there is a relationship, it is not linear. Neither of these have a linear relationship. This has no relationship at all. This has a relationship, but neither of them are linear. So let's go ahead back to the example we did on the previous page, and now let's find the correlation coefficient in Statcrunch for that GPA example. Okay, so according to our notes, we're going to go to Stat, Summary Stats, and then Correlation, and Calculate. So we got to make sure that we select the two components that we want to decide whether it has a relationship or not. So we want to make sure we select those two columns as my X and my Y. So let's go ahead and compute that, and it will give me the correlation coefficient, which is 0.855. So we could definitely say that this is positive, which we knew already because this definitely has a positive relationship. In other words, as the number of hours that you study goes up, obviously so does your GPA. It has a positive linear relationship. Now, how close is it? It is definitely not perfect because it is not 1, but it is very strong. It's close to 0.9, so I would call this a strong positive association. So again, I would describe this association as a strong, positive, linear relation. Once you calculate the linear correlation coefficient, you want to make sure and test it to see if that correlation between those two variables is actually strong enough to conclude that there is a linear relation that exists. So for now, until we can determine that, I can't actually state that there is a linear relation until I plug it into a constraints to determine whether it is. And that's all going to be dependent upon whether I had enough points in my sample. If you only had, for example, to give you an idea of what this means, if I only had, for example, 2 points, I only surveyed 2 people, clearly it's going to look like it has a perfect relation between those 2 points because the only way to connect 2 dots is one straight line. So it gives the illusion that it is a perfect relationship. However, is it strong enough so that we can say that there definitely is a linear relationship amongst all students when all I've surveyed is only 2? So we're going to compare the sample size. In this case, we only had 2 people in our sample. To in the book, there will be a table that will take sample size into consideration. Small sample sizes are usually bad in determining whether there's a linear relationship. If you have a larger sample, then you can usually determine that there is a linear relationship because you've surveyed many, many people. So in order to do that, to test for this, first we're going to determine the absolute value of the correlation coefficient. In this case, the absolute value of R is still 0.855. Then we're going to find the critical value from Table 2 of the appendix for the given sample size. I also have this table posted in the student resources under your modules. If the absolute value of the correlation coefficient is greater than the critical value, we say there is a linear relationship between the two variables. Otherwise, no linear relationship exists. So let's go ahead and first find this critical value in Table 2. So I'm going to pull up the table here. Okay, this is Table 2 from your book. And we're looking for the appropriate N. We had 20 students in our sample. So with 20 students that were in our sample, our critical value for correlation coefficient is going to be 0.444. So let me write that down in the lecture notes. So down here, the critical value is 0.444. And what the notes are telling me to do is the absolute value of the correlation coefficient, is it greater than the critical value? Well, yes, you can see that 0.855 definitely is greater than 0.44. Since it is greater than the critical value, we say a linear relationship exists between the two variables. So since I can now state that there is a linear relationship, I can actually write that in my sentence up here. There is a linear relationship. However, if this happened to go the other direction and the critical value actually was bigger, then we would not be able to say that there was a linear relationship. In other words, your N, your sample size, was too small. Let's try another example. Let's put the data into Excel or Statcrunch from the American Black Bears problem, which is from section 4.1 in the book. So I'm going to go ahead and pull that question up now, and we'll be able to then answer these questions down here. Okay, so I have the book pulled up here, and we're reading this question that says, the website that contained the American black bear data that was listed in problem 28 actually had a bear whose weight is 141 centimeters and weight is 100 kilograms, incorrectly was listed as 41. So we're first going to redraw the scatter diagram, which the original data was back from problem 28. So let me back up a little bit. There we go. Okay, so problem 28 in the book. The American black bear is one of 8 bear species in the world. It is the smallest North American bear and the most common bear species in the planet. In 1969, Dr. Michael P. Pelton of the University of Tennessee initiated a long-term study of the population of the Great Smoky Mountains National Park. And one aspect of the study was to develop a model that could be used to predict the bear's weight, since clearly it's not practical to weigh bears in the field. One variable thought to be related to the weight is obviously the length of the bear. The following data represents the lengths and weights of 12 American bears. So here's the data that we're asked to discuss in this question. So it gives us the length of the bear and how much the weight of the bear was. And we're going to see if the length of the bear is a good predictor of what the weight of the bear might be. So this is going to be my X and this is going to be my Y. So I'm going to go ahead and put this data into Statcrunch, and then we're going to answer some of the questions that were in your lecture notes. Okay, so I put all of the data into Statcrunch. Now remember, anytime that you want to follow along with me in the video, it's always a good time to pause the video and put the information in and try to follow along. So I went ahead and put the data, again, into Statcrunch for the length of each bear and the weight of each bear. In the lecture notes, it asked us, first of all, which variable is the explanatory and which one is the response. In this case, the length would be the x and the weight would be the y. In other words, explanatory and response. Because it specifically said in the question that the scientist wants to measure the length of the bear to guesstimate what the weight of the bear might be. So the weight would be the response. Then it says draw a scatter diagram. So I'm going to go ahead and do that in Statcrunch. We're going to go over here to Graph, Scatter Plot. We're going to select our x variable as the length, and our y will be the weight. So when I go ahead and compute that, I got my scatter diagram that looks like this. So this is going to be the scatter plot of which I'm going to use in my notes. Then we're going to calculate the linear correlation coefficient. So this linear correlation coefficient, how we found that the last time is we went up to summary stats, up to stat, summary stats, correlation, select the two variables, and compute. So here I've got my relationship. Here I've got my correlation coefficient, which is R. And then for the last question, it asks me to decide whether there's a linear relationship between the bears. So now I'm going to go back to my notes to conclude this question. All right, so back to my notes, we decided what the explanatory and the response was. We also drew the scatter plot, which you could do in Excel or you could do by hand using the data from the table. And then we also let Excel find our linear correlation coefficient. I rounded to the nearest thousandths place and made that 0.704. So the next question then asks us, does a linear relationship exist between the weight of a bear and its height? So in order to determine that, we first have to find the critical value of this particular sample. There were 12 black bears in this sample. So if I go to my table here, that is in your book, Table 2 for critical values, it says that the N of 12, in other words, a sample size of 12, has a critical value of 0.576. So that critical value of 0.576, when it is compared to the R that we found as a linear correlation coefficient, you can see that the R is definitely bigger than the critical value from the table. Since it is larger, since the correlation coefficient is big enough in our sample, is bigger than the critical value, then yes, we could say there is a linear relationship. Okay, on to the next page. And the next page we're going to be discussing section 4.2, which is called the least squares regression line. The least squares regression line is a line that minimizes the sum of the squared errors or residuals. This line minimizes the sum of the squared vertical distances between the observed values of y and those that this line is predicted by the line. So let me give you a quick example of what I'm talking about. So in the previous example, we had the black bears, and we had length of the bear, and we have weight of the bear, and then we had a bunch of dots with some sort of a linear relationship. Now, Statcrunch and a formula can determine what is called the least squares regression line. And the least squares regression line will be a line that will best fit all of that data, some sort of a straight linear line that best fits all these data points. It might hit a point, it might not hit any points. But what the line does is it tries to minimize the vertical distance between each point and the line. It wants to minimize this distance, which is called the errors or residuals. So this distance right here is the residual, or the amount of error that the line is making by predicting where this point should be. This point right here had a fairly large residual because it is far from the point, far from the trend line or the regression line. This data point seems to be right on top of the regression line, so therefore it will have a very small error or a small residual. Again, our whole goal is to minimize all of these residuals as much as possible, coming up with this one red line through the data. To do this by hand, the equation of the least squares regression line is given by the following formula. Okay? Y hat equals b1x plus b0. Now this is going to look very, very similar to an equation that you might be familiar with that looks like this. This is slope-intercept form, and that's exactly what this equation is. First thing, we call it y hat instead of y, because y hat is simply just the predictor. As you can see in this graph that I did earlier, this line is the line of y hat. Each of these individual points is the actual value, so it doesn't get the hat, it's the actual y value. However, if I were to predict where this point would be, I predict it would be around here, and the predicted y value would be y hat. It's not the correct value, it's the predicted value. So we've got to specify these y's as different because they very well could be different. Now in this case, our y and our y hat might actually be the same value. Now this predictor line has a slope of b1 and has a y-intercept of b0. We're simply just calling them two different names, but b1 is the slope and b0 is the b. We're going to stay consistent with the way that the book explains slope and y-intercept. So it also goes on to say how we find the slope. The slope is found right here. The slope is found by taking your correlation coefficient and multiplying that by the standard deviation of your y response variable divided by the standard deviation of your x or explanatory variable. And that's the slope of the regression line. Once we find the slope, we can use that down here to find our y-intercept. Our y-intercept is found by taking the average value of all of your response variables, subtracting the slope that we just found up here, times the average of all of the x variables. And this will then give us the y-intercept. And once I have both of those values, I'll then have the equation of the least squares regression line. Now note, you're not going to need to actually calculate this by hand. It's quite a long process. We're going to actually let Statcrunch find this for us, but we are going to do one example in our notes just so you can see how it works. But from here on out, using Statcrunch is going to be a much easier way to find these answers. Okay? On the exam, you're actually going to be given B0 and B1. So, however, even though you will need to know how to put them together to write the equation, let's look at an example of how we could actually do it using the formulas first. Then we'll do another one of what you could actually expect to see on an exam. All right, so below I have an example of a 6 people's credit scores. So down here I have 6 different people and each of their credit scores ranging from not so good to very good. Also on beside that, I've got their interest rates that they're given when they asked for a mortgage loan at their local bank. Clearly, if your credit score is low, you're going to get a high interest rate because you're considered a risky loan. However, if you have a good credit score, you're going to be given a low interest rate. Because your credit is good, you're considered less risky, so they trust you with a lower interest rate as a reward. So right off the bat, we know that this is going to have a negative relationship. Because you can see as the credit score goes up, the interest rate goes down. So when they go opposite directions, this is going to have a negative relationship. So if I were to draw that scatter plot and I were just to do this by hand, which of course we'll do all of this in Statcrunch in a moment, let's put our credit score down here because this is our explanatory variable. It it concludes a response in the interest rate. Our credit scores range anywhere from 550 all the way up to 750. So let's see, we also got 600, 650, 700, and 750. There we go. Okay, our interest rates range anywhere from 5 up to 19. So let's just start at 0. We'll go 5, 10, 15, 20. So our information here, we've got a credit score of 545 with an interest rate of almost 19. So 545 credit rating has an interest rate of 19. A credit score of 595 has an interest rate of almost 18. A credit score of 640 has an interest rate of 12.2. A credit score of 675 has an interest rate of 8.6. An interest rate of 705 has an credit score of 705 has an interest rate of 6.6. And a credit score of 750 has an interest rate of 5.1. So it's very, very linear. Okay, not perfect by any means, but it's definitely got a negative relationship. So first let's find the correlation coefficient from Statcrunch, and then we'll determine whether the linear relationship exists. So at this point I'm going to switch over to Statcrunch. In the meantime, you can put all of this data into Statcrunch and do the rest of this problem yourself. Okay, so I put all of the interest rates and credit scores you could see into Statcrunch here. And so the first thing I'm going to do is I'm going to draw the scatter plot to see that it matches what I drew in our lecture notes. So I'm going to go to Graph, Scatter Plot. I'm going to select the X variable is going to be credit score and the Y will be my interest rate. And you can see that this looks very similar to what we had in the lecture notes. It definitely has a negative relationship. It appears to be linear, but we will prove that when we compare our R against a critical value in a moment. First, let's find the R, which is the linear correlation coefficient. We do that by going to Stat, Summary Stats, Correlation. We select the data, and we compute. So this has a correlation of negative 0.976. That is a very, very high R, or linear correlation coefficient. I would bet that that is going to definitely be a linear relationship. So I'm going to switch back to the lecture notes and let's look at this on paper. So after we drew the scatter plot, which we also did in Statcrunch, we found that the linear correlation coefficient in Statcrunch was negative 0.976. So based on the answer above, is there a linear relationship? Well, you can see that we had 6 individuals, or 6 was our N, or the number in our sample. And if we go to table 2, which was from our book, and we go to an N of 6, you can see that we have a critical value of 0.811. So that's what we need to compare our R to. So what we did here is we compared our R, which is negative 0.976, take the absolute value of that. We want the positive version. We compare that to the critical value in the book, and we see that our R, our linear correlation coefficient, definitely is larger, which means we have enough evidence to prove that there is a linear relationship. Yes. So then we're going to go back to Statcrunch, and we're now going to find what's called the mean and standard deviation of both of the variables, so that way we can plug it up into this formula. Because remember, in order to find this linear regression line, we need to find the slope and the y-intercept. And in order to find the slope and the y-intercept, we need to find the standard deviation of each individual y and x, which is the credit score and the interest rate. We already have R, and then we also need to find the average interest rate and the average credit score. And rather than doing all that by hand, which we certainly can do, we're going to use Statcrunch because it's a tool that we have and it will just make our jobs easier. So the way we're going to do that is go to Statcrunch. So if you want to find specific statistics about a column, what you could do is you could go to your Stat and we're going to go do summary stats by column. So since our data is all listed in a column, we're going to select columns from our summary stats. When we select the columns, we can select the variable in which we want to find the data for. Well, we're going to select both of them because we need both the sample standard deviation and the mean of both of these x and y variables. Okay, so again, I selected one and then I selected the other. So make sure they're both in the square to the right. Then from our table down here, we select the ones that we want. We want to see mean. We also want to see standard deviation. Those are the only two statistics that we actually care about, that we actually want to display in our output. So I'm going to go ahead and compute those, and you'll see that information right here. So for our credit score out of the 6 individuals, we have a mean of 651 out of those 6 people with a standard deviation of 74. Our interest rate has an average of 11.6% with a standard deviation of 5.8. And remember, that's our correlation coefficient. So I'm going to go ahead and jot those down in my lecture notes now. Okay, so I went ahead and I wrote all of that data down that we just found from Statcrunch. We found that the average credit score was 651 with a standard deviation of 74. The average interest rate was 11 and the standard deviation of the interest rate was 5.8. So I wrote all that information down, and I also have my R, which was right here, and those are the 1, 2, 3, 4, 5 pieces of information that we will need in order to find our slope and our y-intercept, which we will do on the next page. So on the next page we have, let's find now the value of the slope. So in order to find the value of the slope, the equation that we had on the previous page said that our slope is found by taking your correlation coefficient times the standard deviation of your response divided by the standard deviation of your explanatory variable. And if we plug all of that data in from the previous page, clearly there will be some rounding because all of these numbers have been rounded from Statcrunch. We can find if we plug all of this into our calculator, we can then find B1, which is the slope of the line. We are expecting a negative value because remember from our picture on the previous page, it definitely had a negative relationship. So our slope is definitely going to be negative. So when I put all of this into my calculator, I'm going to get a slope of negative 0.0764. And at any point during these lecture notes, you should be pausing, finding these numbers, calculating them yourselves, not just writing them down. We're also going to do now finding the y-intercept. The definition for y-intercept from the previous page, B naught, was found by taking the average interest rate minus the slope times the average credit score. So I'd like you to find this information and calculate it. So I put this in my calculator. I find that the y-intercept is 61.39. So to write the full equation for the least squares regression line, remember it's y equals mx plus b, so slope goes first, so it's going to be negative 0.0764 is our slope, plus b, where b is 61.39. So this is the equation of our least squares regression line. And if we were to draw that right on top of our data, it would most likely go right down through the middle of our data points, something like that. So let's check the least squares regression line in Statcrunch by plotting it on top of our data. So according to the notes, we're going to go to Stat, Regression, Simple Linear, and we can then find all of this information there as well. All right, so if we go to Stat Regression, Simple Linear, again, just like we did in the previous example, just like we did over here. In fact, I probably could just do it from here because I already have the graph up. We can just go to our options and edit from there rather than create a whole new graph. I've already got my variables, but the one more thing I would like to do is I would like to add an additional piece of information onto here. Sorry, I'm going to do that one more time. I'm going to redo this. So I'm going to stick with the instructions that says to go to Stat, Regression, Simple Linear. I'm going to select my credit score and my interest rate for my X and my Y. And the last thing I want to do is down here, I want to turn on fitted line plot. In other words, I want to also calculate the line where each the least squares regression line will be on top of my scatter plot. So once I go ahead and compute that, it will give me two things in this box. The first thing it will do is it will give me accurately the y-intercept and the slope. So if in our notes we should go back and check, did we get the slope correct? Negative 0.0764, and that's exactly what we have, and it should match what we did with our equation that we did by hand. Also, our y-intercept of our least squares regression line should be 61.39. Now they rounded 395, which maybe we should have rounded to 40, but we did do it correctly. Okay, so we have both the y-intercept and the slope accurately there. They also write it in a separate place up here if you would like to do it this way instead. It says interest rate, which is your y, is equal to, they put the y-intercept first minus the slope times credit score. So that's just another way of writing it as well there. They also give us some more information. They give us the R, which we already know, we already found. They give us the sample size. And I think that's all that we have talked about so far. But you'll notice down here that they have an arrow. If I click the arrow, it will give me the graph, the scatter plot that we've already created, but this time they plot the least squares regression line right on top of that scatter plot, which is kind of nice. So this is what it would look like if we were to graph both the scatter plot and the line together on one set of axes. All right, so let's go back to the notes. All right, so we verified all of this information. We used Statcrunch and we were able to verify all this. Clearly, all of this you can do in Statcrunch as well. We did one time by hand, but doing it from here on out, we would use Statcrunch to find this example here. But now it's asking us to interpret the slope. So the slope we found earlier was negative 0.0764, and we're asked to interpret that. So if you remember back to what the definition of slope is, it's the change in y divided by the change in x. Okay? So the change in y divided by the change in x. So if our slope by definition is 0.0764, and of course that's over 1, we would describe this as y and x. So remember, y was interest rate and x was credit score. So in an interpretation of that, I would state that for every one change in credit score, so as credit score increases by 1, we could expect interest rates to decrease by 0.0764 percentage points. So if we're asked to interpret the y, okay, the y-intercept if possible, remember the y-intercept, if we were looking at a small little graph right here, it looks like this, where this was interest rates and this was credit score, and it looks like it's crossing right up here at 61. Okay, so what this is saying is as your credit score is 0, we would expect interest rates to be 61.39%. Red flag, this is not appropriate. And a lot of times in this chapter, you will find that the y-intercept is actually not appropriate. You can't have a credit score of 0. This is impossible. Credit scores don't start down at 0. They start at a higher number. No matter how bad you get, it never gets to 0. So that's actually impossible. So this linear regression line actually is only going to be valid between a certain set of numbers. It's not going to be valid all the way back at 0. So if the x simply can't be 0, then you can't technically have a y-intercept that makes any sense. So let's do 2 more questions from the same example. The first one says, predict the interest rate that a person would pay if their FICO score, in other words, credit score, was 723. Well, if we go back to our least squares regression line, let me write it down one more time. I'll just pull it down from up above. And we know that this person's credit score was 723. We're going to take that credit score and we're going to plug it in for x, and we're going to recalculate this. So that means this particular person's y-hat, in other words, predicted interest rate, is going to be at the value of negative 0.0764 times 723 plus 61.39. So when you put that into your calculator, hopefully you'll pause this and find that answer yourself. I'm going to get a value of 6.15%, which is a really good interest rate. But then again, they do have a very good credit score. So last question to this particular problem, okay? Bob has a credit score of 680, which is mediocre. He's offered an interest rate of 8.3%, and he wants to know whether that is a good offer. Okay, so if we look back to the graph that we did earlier, Bob has a credit score of 680, so he's somewhere around here. Okay, and his interest rate, he's getting an interest rate of what did it say? It says he's getting an interest rate of 8.3. So he's getting an interest rate of something around here. This is his actual value right here. I'll circle it in blue. This is Bob. Okay, so here's Bob. He's got a credit score of 680. He is going to get an interest rate of, according to the example, of 8.3. Right here. Here's Bob. It wants to know if Bob's credit score and his interest rate is actually good or bad based on what the average regression line predicts he should be getting. Remember, the red line is his predicted value. They're not going to match up exactly. So let's see where Bob's information is in regards to where he should have been using the prediction line. So let's calculate first where Bob should be. So Bob's predicted interest rate is going to be found by putting his credit score into the regression model. And when we put this into our calculator, he gets an expected 9.44% interest rate, according to my calculator. That's what's expected. But what did he actually get? His y is going to be, was actually 8.3. So see the difference between the predicted and the actual, what he was expected to get and what he actually got. he actually got 8.3. And in this case, a low interest rate is better than a larger one, because remember, you want to pay low amounts of interest, not high amounts. So in this case, Bob actually got a good interest rate. Because he received a lower interest rate than what was predicted. So the last question says, now, what is Bob's residual? Now, residual is how far Bob is from the predictor line. So here's Bob. He received a good interest rate. He is below the prediction line. Well, what is this distance, this vertical distance between Bob's actual and what Bob should have gotten? What is this distance? How far is he off the error from the prediction? We find the residual by taking the actual value. In this case, Bob got an 8.3%, and we minus the predicted value of 9.44. So this particular residual is going to be negative because he's below the predicted regression line, and we would state that Bob's actual score is 1.14% below expected.